There's something that happens to a room when it empties. Not immediately. It takes a moment, a few seconds, maybe, after the last person has gone through the door and the sound of their footsteps has moved far enough away that you stop tracking it. And then the room becomes something else. Not silent, not still, something more particular than that. Something that doesn't quite have a name in ordinary language, which is maybe why most people don't stop to think about it. You felt it. Probably in a kitchen after a dinner that ran late, or an office on a Friday evening, or a school hallway in the summer when the building is technically closed and you're only there to pick something up. The space feels inhabited, even though no one is in it. The air sits differently. There's a faint smell of something, coffee, or the specific dusty warmth of electronics that have been running all day. And the room holds that, keeps it, even after there's nothing left to keep. This is not mysticism. It's not even metaphor, really. It's just a thing that happens to spaces, and most of us notice it without ever pressing on it too hard. But physics, it turns out, has been pressing on it for over a century. The question, and it took a long time before anyone thought to ask it this cleanly, is, what does it mean for a space to be truly empty? Not empty in the everyday sense. Not the room has been cleared out. Empty in the deepest sense available to us. No air, no dust, no light, no heat radiating in from the walls, no stray atoms drifting through. A perfect vacuum, sealed, cooled, stripped of every material thing that can be removed. What is left? The intuitive answer is nothing. That's what nothing means. You remove everything, you get nothing. And for a long time, for most of human intellectual history, honestly, that answer felt obviously correct. Nothing is the baseline. Nothing is what you start with before you add something. Nothing is simple. It is not simple. There's a particular way physics tends to arrive at its stranger conclusions. Not through sudden discovery, not usually. More through a quiet accumulation of results that don't quite fit, measurements that refuse to land where the theory says they should, equations with leftover terms that seem like they should cancel out but stubbornly don't. The strangeness of the vacuum arrived that way, gradually, almost reluctantly, across decades of work in quantum mechanics and thermodynamics and field theory. And what the physics was pointing toward, what it kept circling back to no matter how the question was reframed, was this. A space that has been emptied of everything still contains energy. Not a little. Not residually. Not, well, technically if you're being precise. It contains energy in a way that is irreducible. Energy that cannot be removed because it is not sitting inside the space like furniture that could be carried out. It is the space. It is what space at the quantum level is. That is the thing this chapter is trying to sit near. Let me try to come at it from a different direction, because the vacuum contains energy sounds like a sentence that should be easy to understand and isn't. When you cool something down, you slow it. You take the thermal energy out of its atoms and molecules and they move less. Keep cooling and they move less still. Cool something to absolute zero, the coldest possible temperature, the point at which there is no thermal energy left to remove, and you would expect everything to stop, all motion extinguished. The atoms sitting perfectly still in their perfect cold. That would be truly empty of energy. That would be nothing, but that's not what happens, even at absolute zero. Approached but never actually reached in any laboratory ever. The particles don't stop, they keep moving, just a little, just barely. But they move. This is not instrument error. It is not vibration from the building or heat leaking in through the insulation. It is a genuine, irreducible motion that belongs to the particles themselves, that no amount of cooling will take away. Physicists call it zero-point energy. It's the energy a system has left when you've removed everything you're permitted to remove, the floor below which you cannot go, and when you extend that idea outward, away from a single atom and into the fabric of space itself, you get the quantum vacuum, the thing that remains when everything else has been taken away, the room after everyone has left. There's a quality, and I'm not sure quality is even the right word. It might be more like a behavior, a quality to quantum fields that makes this inevitable rather than accidental. Quantum fields are not like classical fields. A classical field is a value at every point in space, tidy and well-defined, obediently zero when nothing's happening. A quantum field is more trouble than that. It cannot be set to zero and left there. It is subject to something fundamental in quantum mechanics, a principle, Heisenberg's, that says certain pairs of properties cannot both be exactly defined at the same time. Energy and time are one such pair. If you pin down the energy of a region of space with total precision, its behavior in time becomes completely undefined. If you try to force the energy to a perfect zero, you are pinning it as precisely as possible, which means time, the uncertainty, the fluctuation, will be correspondingly wild. The vacuum, therefore, fluctuates. Always. Not because something is wrong with it, because something would be wrong if it didn't. These aren't large fluctuations. They're not the kind of thing you'd notice walking through a room. They operate at scales so small that small itself starts to feel like the wrong word. But they're real, measurable. Their effects show up in the behavior of atoms, in the forces between closely spaced objects, in the accelerating expansion of the universe at its largest scale. The nothing is full. That is the finding. It isn't a metaphor, or maybe it is a metaphor, but it's also just accurate. I find myself returning to that image of the room, the empty kitchen after the dinner, the hallway in the closed school. There's something in it that seems, now, less like feeling and more like a low-resolution perception of something real. The space after everyone has left isn't truly empty. The air itself, the quantum fields threading through it, the zero-point fluctuations rippling at scales far beneath the molecular carries something, has always carried something. We just don't have a word for it in the vocabulary of everyday life. Physics has several. In the chapters ahead, we'll spend time with some of those words. With Heisenberg's principle and what it actually means for a space to have a lower limit on its energy. With the Casimir effect, two metal plates, brought very close together in a vacuum, pulled toward each other by something that is technically nothing. With zero-point energy and absolute zero, and what it means to approach a floor that the universe will never let you reach. But none of that needs to be held right now. For now, there is just this, the room after everyone leaves, the hum beneath the silence, the something that persists when everything removable has been removed. Whether that counts as full depends, perhaps, on what you thought empty was supposed to mean. This project runs without any institutional backing, no grants, no studio, no network. If it has given you something, even just a quieter night, consider supporting it on Patreon. Every contribution goes directly into keeping this space going. The next thing to understand is that this was never supposed to be the answer. For most of history, emptiness was the assumption, the default, the simplest case. The idea that nothing might be doing something wasn't arrived at easily. It had to be forced on physics almost against its will. For a very long time, nobody thought to question it. That's the part that stays with me, honestly. Not the eventual discovery, not the equations, but the sheer duration of the assumption. Thousands of years of philosophy, natural inquiry, early science, and then formal physics, and through almost all of it, emptiness was considered the boring case, the uninteresting one, the thing you wrote in when there was nothing else to write. Empty space was zero. It was the absence of content. It was what you got when you subtracted everything. And that felt not just acceptable, but obvious, self-evidently true in the way that only the deepest assumptions feel obvious. The kind of true that doesn't get examined because examining it seems almost unnecessary, like checking whether the floor is still there when you get out of bed. The ancient Greeks debated the void with unusual intensity for people who had no instruments to probe it. Democritus thought empty space had to exist. Otherwise, how would anything move? You needed gaps between things, vacancies through which matter could shift. His atoms needed room. The void in his picture was not nothing in a rich sense. It was more like a neutral container, necessary but inert, a stage with no properties of its own. Aristotle disagreed, famously, emphatically, in a way that would shape thinking for nearly 2,000 years. Nature, he said, abhors a vacuum. A true void was impossible. Space was always filled with something, air, ether, the medium through which light and influence travelled. For Aristotle, the very idea of a completely empty region was almost incoherent. If there's nothing there, in what sense is there even a location? It's easy to dismiss this now, with the benefit of everything we've learned since. But I find myself, and this is a personal admission, not a rhetorical one, finding Aristotle's position less stupid than I once did. He was wrong, but he was wrong in an interesting direction. He sensed that a void with no properties was conceptually unstable. He just didn't have the tools to find out why. What neither Democritus nor Aristotle could have known, what nobody could have known for a very long time, was that the question, what fills empty space, was not going to have a satisfying answer. It was going to have an unsettling one. The void would turn out not to be filled in the way Aristotle meant, not with some medium, not with ether, not with anything material in the ordinary sense. But it would also turn out not to be empty in the way Democritus needed it to be. Neutral, inert, a blank stage. It would turn out to be neither of those things. It would turn out to be something that didn't fit comfortably into the framework either man was working with, or honestly, into any framework that existed before the 20th century. There's a gap between Aristotle and Newton that's hard to hold in your head, because it spans so many centuries that the human scale of it becomes slippery. Roughly 2,000 years of thinking about space and matter and the void, during which the basic assumption stayed more or less intact. Space is a container. Whatever is in it, the container itself has no physics. It doesn't do anything. It just holds things. Newton's mechanics were built on this assumption. Space in Newton's picture was absolute, fixed, infinite, unchanging, the backdrop against which everything else moved. Time was its own absolute, running independently. And the vacuum, the space between bodies, the gap between the Earth and the Moon, the enormous stretches between stars, was just that. Space. Empty. Without content. This was useful, spectacularly useful. The mathematics of Newtonian mechanics worked, and worked with a precision that still produces a quiet kind of awe when you stop to think about it. The gap between the Earth and the Moon, the orbits of planets, the trajectory of a cannonball, all of it folding neatly into the same equations. And at the centre of all of it, space sitting there, doing nothing, asking nothing of the physics. The emptiness was passive, compliant converse. It held the stage and stayed out of the way. I used to think the shift away from this picture came from Einstein, from relativity, from the idea that space-time curves in response to mass. That the geometry of space itself participates in gravity. That's part of it, genuinely. But that's not where the vacuum's strangeness enters the picture. General relativity curves space but doesn't necessarily fill it. A curved vacuum is still, in some sense, a vacuum. The filling, the discovery that empty space has energy, that it fluctuates, that it cannot be quieted to zero, came from somewhere else. From quantum mechanics, from a set of ideas so structurally different from anything that came before that they didn't just revise the picture of the vacuum, they made the old picture impossible. Here is the thing about quantum mechanics that matters for understanding the vacuum, stated as plainly as I can manage. In quantum mechanics, systems do not simply sit in a state of zero energy when undisturbed. They can't. The mathematics, specifically a relationship known as Heisenberg's uncertainty principle, which connects certain pairs of physical quantities in a deep, non-negotiable way, forbids it. A system at perfect rest with perfectly defined zero energy would require a kind of precision that quantum mechanics structurally does not allow. So every quantum system, every field, every region of space, governed by quantum rules, which is to say, every region of space that exists, retains some energy. Always a minimum, a flaw. This is not a statement about our ignorance. It is not, the system has zero energy but we can't measure it precisely. It is a statement about the system itself. The energy is there, the fluctuations are there, the vacuum is active. Outside right now, wherever you are, the temperature has probably dropped a little since earlier in the day. The kind of drop that makes the air feel slightly more present, more textured, like it has a faint resistance as you move through it. This has nothing to do with what we're talking about, but I find it useful somehow to be aware of physical space while thinking about it. The air in the room, the small sounds from elsewhere in the building, the particular quality of nighttime quiet, because the vacuum we're discussing is not somewhere else. It's not deep space, not the interior of an evacuated chamber in a laboratory. It's here, threading through the room, woven through the space between your hand and the wall beside you. The quantum fields that constitute the vacuum are everywhere, always present, always fluctuating at scales far beneath what any human sense can register. The room that looked empty after everyone left? The physics would say it was never empty, not once, not in any deep sense of the word. What changed between Aristotle and the 20th century wasn't just the accumulation of knowledge. It's more precise to say it was a shift in what physicists were willing to ask. For a long time, the question, what is the vacuum doing, didn't get asked, because the answer was assumed to be nothing by definition. The vacuum was the thing that wasn't doing anything. That was its entire job. Quantum mechanics made the question unavoidable. Once you accept the uncertainty principle, and the evidence for it is relentless, comprehensive, built from decades of extremely precise measurement, you cannot also accept a vacuum that sits in perfect stillness. The two things are incompatible. The principle demands activity, demands it from everything, including from nothing. And that's the point at which the assumption cracked. Quietly in equations, in small discrepancies between theoretical predictions and laboratory measurements. Not in a sudden dramatic moment. More like a sentence you've been reading one way for years, until one afternoon you read it again and realize it means something completely different. The assumption that nothing is the simple case is deeply wired into ordinary thinking. We begin from zero and add. We clear a space before we build. We empty a cup before we refill it. The blank, the void, the absence. These feel like starting conditions, like what you have before physics applies. But physics applies to the vacuum too. That is the conclusion 2,000 years of slowly shifting thinking arrived at. The vacuum is not exempt. It is not outside the rules. And the rules say, no energy can be reduced to nothing. There is always something, a residue, a flaw, Not a metaphor for existence, not a philosophical position about the nature of being, just a measurable, undeniable, stubborn physical fact. The nothing never was nothing. It was just quiet enough that no one heard it. Max Planck heard something in 1911. Not the full picture, nobody had that yet, but a term in his equations that didn't go away when it should have. A small persistent quantity that sat at the bottom of the math like sediment that wouldn't clear. He called it zero-point energy, half tentatively, not entirely sure what he was naming. What it would eventually mean for the vacuum, for the structure of space itself, for the energy density of the entire observable universe, none of that was visible yet. But the term was there, sitting in the equation, refusing to be zero. Put your hand flat on a table, not to feel anything specific, just put it there. Feel the surface under your palm, the slight give of skin against something that doesn't give at all. The table is solid. It feels inert. It feels like it is doing nothing, which is pretty much what tables are supposed to do. Now hold that image because it's about to become useful in a way that has nothing to do with furniture. The table is not doing nothing. At the atomic level, it is a dense, almost violent negotiation of electromagnetic forces, electrons repelling electrons, nuclei held in lattice arrangements by quantum rules, thermal vibrations passing through the crystal structure like slow ripples. None of this is visible. None of it is felt. Not really, not as individual events. What you feel is the macroscopic average of an enormous number of tiny processes, and that average feels solid and still and inert. The vacuum is something like this. Not identical, the analogy wears out quickly if you push it. But the basic principle carries. What looks still from the outside is not, in any deep sense, actually still. A quantum field is not a thing in the way the table is a thing. It doesn't have edges. It doesn't sit in space so much as it constitutes space, or at least, and this is where the language starts to strain, it is present at every point in space simultaneously, carrying values that describe the likelihood of particles appearing, the strength of forces, the shape of interactions. Every particle you've ever heard of corresponds to a field. The electron has a field, the photon has a field, the quarks inside protons have fields. These fields are everywhere, all of them, all the time, and none of them can be turned off. That last part is the one that takes a moment. You can reduce a field's activity. You can cool a region of space, remove particles, suppress interactions, get the field into what physicists call the ground state, its lowest possible energy configuration. This is as quiet as the field gets, as close to zero as it can come. But ground state is not zero state. This is the thing. The ground state of a quantum field still contains energy, still fluctuates. The field in its quietest possible condition is still doing something, still carrying this irreducible, unkillable restlessness that the mathematics of quantum mechanics says cannot be removed. Restless is honestly the right word for it. Not anxious, not violent, just constitutionally incapable of stillness. Like someone who can sleep deeply but always with some small movement, a shift of weight, a finger twitching. The deep sleep is real. The stillness is not complete. Why? The honest answer involves the uncertainty principle, which will get more space later in these pages. But the short version, the version that matters here, in quantum mechanics, energy and time are linked in a specific non-negotiable way. To have precisely zero energy, exactly zero, not approximately, you would need perfect certainty about the field's energy value at every moment, and perfect certainty of that kind is forbidden. It would violate the structure of the theory at the deepest level, So the field fluctuates, not because something is disturbing it from outside, because its own quantum nature demands fluctuation. The uncertainty is baked in, not added on. I find myself wanting to resist this, even now, knowing it's correct. There's something in ordinary intuition that insists zero should be achievable. That if you remove enough, eventually you get to nothing. That the process of subtraction has a terminus. Quantum mechanics says, not for fields, not ever. The terminus keeps retreating. There's a smell, faintly, in the room where I tend to think about this kind of thing, of old paper and whatever the heating system runs on, something slightly metallic that only appears when the radiator clicks on after being off for a while. It has nothing to do with quantum fields. But there's something in that smell, in the way a space that seemed dormant suddenly announces itself, that feels adjacent to what we're talking about. The thing you didn't notice was running the whole time. Now, the vacuum. The quantum vacuum is what you get when you take a region of space and remove everything you're able to remove. All particles, all radiation, all thermal energy, everything extractable, extracted. What remains is not nothing. What remains is the ground state of every quantum field that exists, and there are many, all of them sitting at their minimum energy, all of them still fluctuating, still humming at that irreducible floor. This is not an exotic condition, it is the default condition of space. The vacuum is not a special state you have to engineer. It's what space is when you leave it alone. Every cubic centimetre of empty space, the space between your hand and the wall, the space inside the room you're in, the space between galaxies, is threaded with these fields. All of them in ground state, all of them fluctuating. The vacuum energy is not somewhere else, in some laboratory, in some evacuated chamber. It's here. It's always been here. It was here before the lamp was turned on, and it will be here after. A quantum field is not a wave, not exactly. It's not a particle either. It's something that, depending on what you're asking of it, depending on how you look, can produce wave-like or particle-like behavior, but is neither of those things in its raw form. The field itself is more like a propensity, a structured tendency. Every point in space carries a value for the field, and that value is uncertain, quantum mechanically uncertain, and the uncertainty means energy, and the energy cannot be removed. Calling it a field is just the best word available. It's a placeholder that has become so embedded in the physics that it's stopped feeling like a placeholder. What the ground state fluctuations actually look like, if look like means anything at these scales, is a topic that gets complicated fast. Virtual particles are often invoked here, and they're not wrong exactly, but they're also not quite right in the way the term suggests. We'll spend more time with them. For now, just the field, just the fact that it's there, active, carrying energy in its quietest state. One thing that took me longer to absorb than I'd like to admit: the fluctuations are not small in some absolute sense. They are small compared to everyday energies. But across all of space, across every field summed up, the total energy is not small. It's not small at all. The vacuum might contain more energy than everything else in the universe combined. Might. The calculation is genuinely difficult. And the answer, when theorists try to compute it from first principles, comes out disturbingly, almost embarrassingly wrong in a way that is itself one of the deepest unsolved problems in physics. But that comes later. For now, the quieter fact. The fields are on. They were never off. They are running right now, through the space in this room, through the space inside your body, through the space between every atom of every object you have ever touched. There is no switch. There was never a switch. The hum you don't hear isn't silence. It's a frequency below what listening can reach. This is where the physics starts to get specific in a way that the vague image of fields everywhere doesn't fully prepare you for. Because the claim isn't just that fields exist and fluctuate. The claim is that these fluctuations have measurable consequences, that they push on things, that they show up in experiments in the behavior of atoms, in forces between objects separated by empty space. The vacuum, it turns out, is not just philosophically interesting. It acts, it exists, it leaves marks on the physical world that can be measured with enough care and the right equipment. 2 metal plates in a vacuum would like to show you something. In 1911, a physicist sitting somewhere in Berlin, at a desk presumably, with paper and whatever instruments of thought a theoretical physicist of that era kept close, wrote down a formula. The formula was a revision of something he'd already published. He was trying to describe the way energy distributes itself across the frequencies of radiation, trying to get the mathematics to match what experiments were showing. He'd done this before, successfully in 1900, and that earlier version had already changed physics more than most people understood yet. But something in the 1900 version had been bothering him, a conceptual discomfort he couldn't fully articulate. So he revised it, and in the revised version, quietly, almost as a byproduct of the adjustment he was making, a small term appeared at the bottom of the expression, a term that represented energy remaining in a system even when that system had been cooled all the way down. Energy at the 0 point of temperature. He called it plainly 0 point energy, Nullpunkt energy in the German. He wasn't sure what to do with it. That's the part that doesn't get mentioned enough. Planck added the term, saw it, understood that it described something real in the mathematics, and then largely set it aside. Not dismissed, not deleted. He left it in the equation. But he didn't press on it with the full weight of his attention, didn't chase it into its stranger implications, didn't ask what it would mean if you extended the idea beyond a box of radiation and out into the fabric of space itself. He had other things to think about. Quantum mechanics was barely a word yet. The conceptual infrastructure that would eventually make 0 point energy not just mathematically permissible but physically mandatory, that didn't exist in 1911 in anything like its complete form. Planck had the term. He didn't yet have the theory that would explain why the term had to be there. This is how a lot of physics actually moves. Not cleanly, not in sudden leaps of complete understanding, but in this more halting way, where someone writes something true, and the truth of it is visible in the math, long before anyone can explain what it means. Outside tonight, there's probably some version of the ordinary world going on. A car passing, the sound of something settling in the walls of the building. These small sounds that make a quiet room feel more quiet rather than less, the way distant noise sometimes does that. 0 point energy in Planck's 1911 paper referred specifically to the energy of oscillators, mathematical representations of how systems vibrate at absolute 0 temperature. The term described the residual energy those oscillators would carry even when all thermal motion had been removed. It was a quantum correction, emerging from the new quantization rules Planck had been developing. What it would eventually mean, after Heisenberg and Schrödinger and Dirac, after quantum field theory developed across the following decades, is something considerably larger and stranger than what Planck was describing in 1911. The 0 point energy of quantum field theory is not just the residual wiggle of an oscillator. It is the irreducible energy of space itself, present everywhere, woven into the ground state of every quantum field that exists. Planck's term was the first glimpse of that. A small patient quantity at the bottom of an equation, waiting for the rest of physics to catch up to what it was pointing at. Patient is the right word, not dramatic. It didn't announce itself. The term sat in the equation. Physics moved around it, through it, past it. Quantum mechanics developed through the 1920s, and the concept of zero-point energy came with it, growing in theoretical importance, understood more deeply as the structure of quantum theory solidified. Einstein took it seriously, which meant others did too, eventually. Experiments were designed to test for its effects, and slowly, across decades, a picture assembled. The zero-point energy is real, measurable, not an artifact of the math, but a feature of physical reality. What Planck had written in 1911, in other words, was not wrong. Nor was it, and this is the correction I want to make carefully, exactly right in the way he intended. The term survived, but it survived into a theory he couldn't have fully anticipated. The zero-point energy of quantum field theory is related to his term the way a river is related to the spring that feeds it. Connected, traceable, but much larger than the source. Is that a fair way to put it? I think so, though fair is a strange criterion for physics. There's something that strikes me returning to this moment. A man at a desk, revising an equation, leaving a term in because the mathematics required it, about the relationship between writing something down and understanding what you've written. Planck understood his equation. He understood the mathematics. What he couldn't have understood was where the term would end up. In the foundations of quantum field theory, in the explanation of the Casimir effect, in the theoretical underpinning of the vacuum energy of the universe. The term he left in the formula in 1911 is, in a direct sense, the same concept that cosmologists now invoke when they try to explain why the universe is accelerating its expansion. He wrote it down because the math needed it. The math turned out to know something he didn't yet. This is a short chapter. It's supposed to be. Some ideas don't need a long approach. Some moments in physics are small enough to hold in one hand, a single term in a single paper in a single year, and the right response is to hold them for a moment without adding much. The zero-point energy of 1911 is one of those moments, a term that survived, that grew. That turned out to mean considerably more than the equation it came from, and if there's a topic you'd like this space to explore, something specific in physics or the universe that you've been quietly curious about, you can leave that request over on Patreon, where this work is supported. The next thing to understand, really sit with, is what happens when you try to reach the floor the term was pointing at. When you actually cool something down as far as physics will allow, and watch what the system does when it should, by all ordinary intuition, go completely still. It doesn't go still. What happens instead is stranger than quiet. There is a specific quality to serious cold, not the cold of a winter morning, which is uncomfortable but alive, which bites and stings and in its own way feels full of something. A different cold. The cold of a walk-in freezer maybe, or a hospital basement corridor at 3 a.m. A cold that is flat, that seems to suppress rather than stimulate, that makes the air feel thin and indifferent. The kind of cold that doesn't seem to want anything from you. Physicists have spent a very long time trying to make things colder than that. The idea of temperature has a direction built into it, which is easy to miss because we experience it mostly from the middle. Things can be hot, arbitrarily, enormously hot, no apparent ceiling. Stars reach tens of millions of degrees in their cores. The early universe was hotter still by factors that become abstract almost immediately. But cold has a bottom. Cold has a limit. That limit is absolute zero. 0 on the Kelvin scale, minus 273.15 degrees Celsius. The temperature at which, in the classical picture, the picture that made sense before quantum mechanics, all thermal motion would cease. Every atom, every molecule, every vibrating particle in every material would come to a complete stop. No kinetic energy, no jostling, no heat in any form, just stillness. It's a clean concept, satisfying in its finality, a true zero, not a conventional one. It is also, in practice, unreachable. This is not a technological limitation in the ordinary sense, not the kind of problem that more funding or better engineering would eventually solve. It is a fundamental constraint built into the structure of thermodynamics. To cool something, you need to move its heat somewhere else, and that process becomes progressively, asymptotically harder as you approach absolute zero. Each step downward costs more than the step before. The last fraction of a degree would require infinite resources, so physicists approach it. They get extraordinarily close. Laboratories around the world have cooled small samples of matter to temperatures measured in nanokelvins, billionths of a degree above absolute zero. Temperatures so low that the thermal energy left in the sample is almost incomprehensibly small. Clouds of atoms held in magnetic traps, bowed by precisely tuned laser light, cooled to a stillness so complete that the atoms begin behaving in collective ways that have no analogue in ordinary experience, forming states of matter that don't occur anywhere in nature, existing only because a small group of physicists in a basement somewhere decided to see what happened if they made something this cold. What they found, consistently, every time, at every scale, with every method, the atoms did not stop. They slowed. Dramatically, more than almost anything in the natural universe. But they didn't stop. They retained a faint, irreducible motion that persisted, regardless of how much thermal energy was removed. A motion that cooling could not touch because it was not thermal in origin. It didn't belong to the heat. It was something else. This is what zero-point energy looks like from the outside, if "looks like" is even a useful phrase here. Not a glow, not a visible shimmer. Just the stubborn, quiet refusal of matter to go completely still, no matter how far down the temperature scale you push it. There is a glass of water. This is a strange and specific detail, but there is a glass of water on the table near where I'm trying to think through this, and it has been sitting there long enough to reach the temperature of the room, perfectly still on the surface, nothing moving that you could see, and yet every molecule in it is in motion. Fast, random, incessant motion at the molecular level. Room temperature, by the standards of what we're discussing, is almost unimaginably hot. The quantum mechanical explanation for why the motion persists begins with something that initially seems unrelated: the shape of the mathematical description of a particle in a confined space. In quantum mechanics, particles don't have fixed positions and velocities the way classical objects do. They're described by wave functions, mathematical objects that encode the probability of finding the particle in different states if you were to measure it. And wave functions, unlike classical trajectories, cannot be flat. They oscillate. They have a natural curvature built into them. A wave function cannot be drawn as a perfectly horizontal line because the mathematics forbids it. The same way a vibrating string cannot rest at exactly zero displacement everywhere along its length, while still satisfying the wave equation. The consequence of this, applied to energy, is direct. The lowest energy state of any quantum system is not a state of zero energy. The wave function in its ground configuration still has curvature, still oscillates, and that oscillation corresponds to energy. Minimum energy, irreducible energy, energy that is not thermal, not kinetic in the everyday sense, but genuinely physically present. Zero-point energy is, in this sense, the energy cost of being a quantum system. The price of existing in a universe governed by wave mechanics rather than classical mechanics. Every particle pays it. Every field pays it. There is no exemption. What I find myself reluctant to accept, and this reluctance is honest, not rhetorical, is the implied consequence when you extend this from a single particle to a field spread across all of space. Because a quantum field is not one oscillator. It is, mathematically, an infinite collection of them, one at every point in space, all of them in ground state, all of them carrying their 0-point energy. Sum them up and you get, well, the calculation diverges. It gives infinity. Or if you introduce a cutoff, it gives a number so large that comparing it to anything measured in the real universe produces a ratio that is embarrassing to write down. This is a real problem, not a solved one, but it comes later. For now, just the cold. The laboratory's chilled to nanokelvins. The atoms nearly still, suspended in magnetic fields, slowed by lasers to a crawl that has no equivalent in nature. And underneath that crawl, underneath the last traces of thermal motion, something that refuses to quiet. Absolute zero is a horizon. That's the most honest description I can offer, though honest and metaphor don't always sit comfortably together, and I'm aware this one has limits. Horizon that moves as you move toward it, always the same distance away, no matter how much ground you've covered. Not because of some external resistance, not because the universe is withholding anything, because the structure of quantum mechanics means the floor is not a fixed location. It is always just beneath wherever you are. The atoms keep moving, the fields keep fluctuating, the ground state hums at whatever scale you look, in whatever material, in whatever region of space, in whatever corner of the universe. Cold, it turns out, has a bottom. But the bottom is not still. That distinction between the lowest possible energy and zero energy is the whole story. The rest is details, extraordinarily interesting details, but all of them follow from this, that the minimum is not nothing, that below temperature, below heat, below all the ordinary ways energy moves and transfers and dissipates, there is something that remains, not warm, not active in any sense your body would register, but present. The floor exists, and the floor hums. Proving that took more than a theoretical argument. It took a measurement, one of the more quietly remarkable measurements in the history of physics, that didn't involve cooling anything at all. It involved two metal plates, a perfect vacuum, and a force that, by every classical expectation, should not have existed. Start with the setup, because the setup is everything here. Two metal plates, flat, parallel, polished, smooth, separated by a gap. Not a large gap, nothing you could see without magnification, somewhere in the range of a few hundred nanometers, which is smaller than the wavelength of visible light. The plates are placed inside a chamber. The chamber is evacuated, the air is removed, the stray molecules cleared out, the pressure brought as low as current technology allows. The two plates now face each other across a gap that is, by any reasonable description, empty, and then they are released and allowed to do whatever they will do on their own. The prediction, if you're working from classical physics, from the physics of the 19th century before quantum mechanics rewrote the rules, is straightforward. Nothing happens. The plates are electrically neutral. There is no charge between them, no magnetic field pulling them together, no residual gas to push them. The vacuum between them is empty. Empty space exerts no force. The plates should simply remain where they are, motionless, indefinitely. That is not what happens. The plates move toward each other. Something in the nothing between them pushes, or pulls, depending on how you frame it, them together. A measurable force. Weak, at the scales where this effect is most cleanly observed, but real, reproducible, precise enough that, in careful experiments, it matches theoretical predictions to within experimental error, a force that has no source in the classical sense, no charge, no field in the ordinary meaning of that word, no particle travelling between the plates and striking them, just the gap, just the vacuum, just something that the vacuum is doing that it shouldn't, by classical expectation, be doing at all. This is the Casimir effect, named for the Dutch physicist Hendrik Casimir, who predicted it theoretically in 1948. He was working through the quantum mechanics of the electromagnetic field, the quantum vacuum specifically, and realized that the presence of two conducting plates would alter the structure of the vacuum fluctuations in the gap between them. Here is the core of it, stated as plainly as I can. The quantum vacuum is not uniform. It fluctuates, constantly, everywhere, at all frequencies, but the frequencies it can support are not the same everywhere. Between two conducting plates, the electromagnetic field is constrained. Only certain wavelengths fit in the gap, the way only certain notes resonate cleanly in a specific room. Wavelengths that don't fit the geometry are suppressed. Outside the plates, the vacuum fluctuates freely, at all frequencies, without restriction. Inside the gap, some of those frequencies are missing. More fluctuations outside than inside. That imbalance, and this is the part that requires a moment to sit with, creates a net pressure. The unrestricted vacuum outside pushes in with more energy than the restricted vacuum inside can push back, and so the plates feel a force, not from anything material, from the geometry of what the vacuum is permitted to do in different regions of space. The force is real. It has been measured. First confirmed experimentally in a careful way by Steve Lamoureux in 1997, and subsequently refined and verified by multiple independent groups. The numbers match the theory. The effect is not subtle in the sense of being unclear. It is subtle in the sense of being small, which is different. At separations of around 10 nanometers, the pressure becomes comparable to atmospheric pressure, not negligible. The thing I keep returning to, and I'm not sure returning to it resolves anything, is what this experiment is actually demonstrating. It is not demonstrating that there is some hidden material in the vacuum. No new particles, no undiscovered field in the exotic sense. It is demonstrating that the quantum vacuum itself, the ground state of the electromagnetic field, the state that exists when you have removed everything removable, exerts force, has energy, is not passive. The vacuum is doing something. I want to be careful not to overstate this. Careful, and also aware that the temptation to overstate it is understandable, because the result is genuinely striking. The Casimir effect does not prove that the vacuum contains infinite energy, or that it can be harvested, or that the nothing between the plates is secretly a something in any exotic new sense. What it proves is narrower and, I think, stranger. That the structure of the vacuum, specifically the frequencies of its fluctuations, the geometry of what it can and cannot do in a given region, affects the physical world directly. That two objects can exert force on each other through a perfect vacuum with no material intermediary, purely because the vacuum between them is different from the vacuum around them. The heating unit in the building where I used to work had a particular rhythm. 3 clicks, a pause, a low hum that would build for about 4 seconds before stabilizing. You stopped noticing it after a few weeks. Then one evening it didn't come on, and the silence was suddenly obvious in a way the sound never had been. The absence of a background you'd stopped registering. What the Casimir effect is not, because this matters for clarity. It is not static electricity. The plates in a properly conducted experiment are neutral, grounded, chosen specifically to eliminate electrostatic contributions. It is not van der Waals force in the ordinary molecular sense, though the relationship between the Casimir effect and van der Waals forces at different scales is a real and interesting part of the theoretical picture. It is not gravity. It is not caused by residual gas molecules at low vacuum. Each of these alternatives has been tested, controlled for, eliminated. What remains is the vacuum. What remains more precisely is the energy of the vacuum, and the fact that the vacuum between two conducting plates is not the same vacuum as the vacuum outside them. The boundary conditions matter. The geometry matters. The structure of the fluctuations matters. Nothing apparently has a structure. Casimir himself, working in 1948, was building on an understanding of the quantum vacuum that was still relatively new. Quantum electrodynamics had only recently been placed on solid theoretical footing, and the full implications of vacuum fluctuations were still being worked out. He did the calculation, found a finite attractive force, and published it. It was a prediction made from the theory, before the experimental confirmation, which wouldn't come for nearly 50 years. 50 years is a long time to wait for a measurement. The measurement, when it came, was worth waiting for. 2 flat surfaces, a gap measured in nanometers, a vacuum as complete as the apparatus could achieve, and a force, small, steady, uninvited, pulling them together across empty space. The empty space did that. That is the whole fact. The Casimir effect is in one sense a laboratory curiosity, a delicate measurement requiring precise conditions, producing forces relevant mainly at scales far below what you would ordinarily encounter. But in another sense, it is something more significant than that. It is the clearest, most direct demonstration that the quantum vacuum is not a theoretical abstraction. It is physical. It acts. It participates in the mechanics of the world. The nothing between the plates is not doing nothing. It never was. And there is a reason the vacuum has this structure, a reason it fluctuates at all, a reason it cannot be brought to zero regardless of how thoroughly you evacuate the space or how carefully you cool the surroundings. That reason is not engineering. It is not the limitations of experiment. It is woven into the foundational rules of quantum mechanics, into a principle so deep and so general that its implications reach from the behavior of individual atoms to the large-scale structure of the universe. The plates showed that the vacuum acts. What comes next is why it has no choice. Most people, when they first encounter Heisenberg's uncertainty principle, file it under a reasonable-sounding category, the limits of measurement. The idea being that particles are small, our instruments are clumsy, and when you try to pin down exactly where something is, the act of looking disturbs it. You shine light on an electron to find it, the photon knocks it sideways, and now you've changed its momentum by trying to measure its position. The uncertainty, in this reading, is a practical problem, a technical one, the kind of thing that better instruments might one day reduce, if not eliminate. This reading is wrong. Not wrong in a subtle, technical, quibble-worthy sense. Wrong in the sense that it describes a different phenomenon entirely. The uncertainty Heisenberg identified is not about the clumsiness of instruments. It is not about the disturbance caused by observation. It is not a statement about what we can know. It is a statement about what is. The distinction matters enormously for understanding the vacuum, so it's worth staying with for a moment. In the classical picture of physics, the picture that works beautifully for objects at human scales, for cannonballs and planets and anything you can hold in your hand. Objects have definite properties. A ball has a position, it has a velocity. Both are fixed, both are real. Both could in principle be measured with arbitrary precision if your instruments were good enough. The uncertainty in your measurement is about you, not about the ball. In quantum mechanics, this is not the situation. A quantum particle does not have a definite position and a definite momentum simultaneously. Not because we can't measure both at once, because both don't exist simultaneously. The position is not a hidden fact waiting to be uncovered. The momentum is not secretly fixed while we look away. These properties are genuinely, physically indefinite until measured, and the relationship between how indefinite they are is governed by a precise mathematical inequality. This is not a philosophical interpretation. It is built into the formal structure of quantum mechanics in a way that has been tested to extraordinary precision and has never been violated by experiment. The inequality itself, the mathematical statement of the uncertainty principle, says, roughly, that the product of the uncertainty in position and the uncertainty in momentum cannot be smaller than a certain fixed quantity. Make the position more definite and the momentum becomes less definite. Make the momentum sharp and precise and the position spreads out, becomes diffuse, loses resolution. The two quantities trade off against each other in a relationship that has nothing to do with instruments and everything to do with the wave nature of quantum systems. There is an equivalent relationship between energy and time. If you want to know the energy of a system with great precision, you need to observe it over a long time. If your observation window is short, the energy becomes uncertain, spread across a range. Pin the time interval down tightly and the energy blurs. Let the time extend and the energy sharpens. This is the version of the principle that reaches directly into the vacuum. Think about what it would mean for a region of space to have exactly zero energy. Not approximately zero, not very close to zero, exactly, perfectly, precisely zero. The number zero, with no uncertainty, no spread, no range. Zero with total confidence. For that to be true, the energy would have to be perfectly defined. And for the energy to be perfectly defined, by the energy-time uncertainty relation, the system would need to be observed over an infinitely long time. Or, equivalently, the energy would need to be absolutely fixed with no fluctuation for all of eternity. But a quantum field cannot be absolutely fixed. The uncertainty principle forbids it. The energy of the field at any given moment has an inherent spread, a quantum blur that cannot be reduced to zero without violating the mathematics of the theory. Exact zero is not a state the field can occupy. It would require a certainty that quantum mechanics does not permit. Therefore the field fluctuates, not sometimes, not under certain conditions, always, as a matter of structural necessity, as a consequence of the same mathematics that governs atoms, electrons, photons, everything quantum mechanics describes. The vacuum fluctuates because the vacuum is a quantum system, and quantum systems do not sit at exact zero. I remember the first time this actually settled in my thinking, not as a fact to be filed, but as something that genuinely shifted the picture. It took longer than I'd like to admit. The phrase quantum fluctuations gets used so often, in so many different contexts, that it can start to feel like a label rather than a description. A placeholder for strangeness, not an explanation of it. There is a kind of transaction that happens so fast that by the time you might notice it, it's already over. Not a metaphor exactly, or not only a metaphor. In the quantum vacuum, energy appears and disappears at timescales so short that short is almost the wrong word for it. The intervals involved are so brief that they sit below the threshold of anything measurable by any instrument, below the resolution of any clock, below the floor of what can be directly observed. And yet the physics says something is happening there. The word that gets used is virtual particles, and the word is, this is where I want to be careful, because virtual in everyday language means simulated, not real, existing only as a representation of something else. A virtual meeting is not a real meeting. A virtual object in a video game is not a real object. Virtual particles are not like that. They are not simulations. They are not placeholders. They are not a way of saying, imagine as if particles were appearing, while what's really happening is something else. The term comes from the mathematics of quantum field theory, where certain terms in the calculation describe particle-like excitations that don't persist long enough to be detected directly. They are real in the sense that their effects are real. They show up in calculations, and those calculations match experiments. They just don't persist. The virtual means something closer to existing outside the conditions required for direct observation. Here is the mechanism, stated as simply as I can manage it. The uncertainty principle, the energy-time version of it, permits a fluctuation in the energy of the vacuum over a short enough interval. A brief spike, a momentary departure from the ground state, a small loan of energy from somewhere. The mathematics doesn't specify a lender. The energy appears. A particle and its antiparticle flicker into existence, both required because the creation must conserve the relevant quantities. They exist for a time inversely proportional to their energy. The more massive the pair, the shorter their existence. Then they annihilate, recombine, return the energy, the books balance. All of this happens below the threshold at which the uncertainty principle would be violated. The debt is paid back before the universe in some sense notices it was borrowed. I almost want to compare this to something more familiar, but every comparison I reach for distorts it in some specific way that seems worse than no comparison, so I'll leave it as it is, an event that occurs, a pair that exists, a return that completes it. The language strains here not because the physics is vague, but because the physics is precise in a register that ordinary language wasn't built for. A candle was burning somewhere, earlier this evening, not here, somewhere nearby, carried in briefly and then taken out, and the smell of it is still faint in the air, wax and a thin thread of smoke, already almost gone. The important thing, and this might be the central thing in this entire short chapter, is that virtual particles are not nothing. Their effects are measurable. The Casimir force between two metal plates is partly understood in terms of virtual photons, the virtual excitations of the electromagnetic field being suppressed in the gap between the plates. The Lamb shift in hydrogen, a tiny but precise displacement in the energy levels of the atom, is caused in part by virtual particles in the vacuum interacting with the atom's electron. These effects are small. They are also among the most precisely confirmed predictions in all of physics. So whatever virtual means in the context of quantum field theory, it does not mean inconsequential, it does not mean absent. It means something closer to present, but briefly. Present, but in a way the usual rules of detection cannot catch. Real, not real. Provisional. That last word is the one I keep coming back to. Virtual particles occupy a category that sits uncomfortably between existence and non-existence in the way everyday language draws that line. They participate in physics. They leave marks. And they do so without ever crossing the threshold that would make them directly observable as individual events. There is a kind of transaction that happens so fast that by the time you might notice it, it's already over. not a metaphor exactly, or not only a metaphor. In the quantum vacuum, energy appears and disappears at timescales so short that short is almost the wrong word for it. The intervals involved are so brief that they sit below the threshold of anything measurable by any instrument, below the resolution of any clock, below the floor of what can be directly observed. And yet the physics says something is happening there. The word that gets used is virtual particles, and the word is, this is where I want to be careful, because virtual in everyday language means simulated, not real, existing only as a representation of something else. A virtual meeting is not a real meeting. A virtual object in a video game is not a real object. Virtual particles are not like that. They are not simulations. They are not placeholders. They are not a way of saying, imagine as if particles were appearing, while what's really happening is something else. The term comes from the mathematics of quantum field theory, where certain terms in the calculation describe particle-like excitations that don't persist long enough to be detected directly. They are real in the sense that their effects are real. They show up in calculations, and those calculations match experiments. They just don't persist. The virtual means something closer to existing outside the conditions required for direct observation. Here is the mechanism, stated as simply as I can manage it. The uncertainty principle, the energy-time version of it, permits a fluctuation in the energy of the vacuum over a short enough interval. A brief spike, a momentary departure from the ground state. A small loan of energy from somewhere. The mathematics doesn't specify a lender. The energy appears. A particle and its antiparticle flicker into existence, both required because the creation must conserve the relevant quantities. They exist for a time inversely proportional to their energy. The more massive the pair, the shorter their existence. Then they annihilate, recombine, return the energy, the books balance. All of this happens below the threshold at which the uncertainty principle would be violated. The debt is paid back before the universe in some sense notices it was borrowed. I almost want to compare this to something more familiar, but every comparison I reach for distorts it in some specific way that seems worse than no comparison, so I'll leave it as it is, an event that occurs, a pair that exists, a return that completes it. The language strains here not because the physics is vague, but because the physics is precise in a register that ordinary language wasn't built for. A candle was burning somewhere, earlier this evening, not here, somewhere nearby, carried in briefly and then taken out, and the smell of it is still faint in the air, wax and a thin thread of smoke, already almost gone. The important thing, and this might be the central thing in this entire short chapter, is that virtual particles are not nothing. Their effects are measurable. The Casimir force between two metal plates is partly understood in terms of virtual photons, the virtual excitations of the electromagnetic field being suppressed in the gap between the plates. The Lamb shift in hydrogen, a tiny but precise displacement in the energy levels of the atom, is caused in part by virtual particles in the vacuum interacting with the atom's electron. These effects are small. They are also among the most precisely confirmed predictions in all of physics. So whatever virtual means in the context of quantum field theory, it does not mean inconsequential, it does not mean absent, it means something closer to present, but briefly. Present, but in a way the usual rules of detection cannot catch. Real, not real. Provisional. That last word is the one I keep coming back to. Virtual particles occupy a category that sits uncomfortably between existence and non-existence in the way everyday language draws that line. They participate in physics. They leave marks. And they do so without ever crossing the threshold that would make them directly observable as individual events. The vacuum is full of them. Every point in space, every quantum field, every moment. This churn of provisional existence, borrowings and return, pairs appearing and annihilating below the floor of what can be directly seen. Whether that constitutes something depends on what you mean by the word. Physics at this point has largely stopped asking whether it constitutes something. It asks instead what it does, what its effects are, how precisely those effects can be calculated and measured. The question of whether virtual particles really exist is, in some sense, a philosophical one that the physics has decided it doesn't need to resolve in order to proceed. The effects exist. That much is settled. What those effects do to the simplest atom in existence, to hydrogen sitting quietly in its ground state, its single electron in its lowest energy level, is something that took extraordinarily delicate measurement to detect. A shift so small that it had been hiding inside the margins of earlier experiments. A displacement in an energy level that should, by the equations available before 1947, have been exactly zero. It was not zero, it was never zero. Before 1947, the hydrogen atom was considered, in a specific and important sense, solved. Not completely. Nothing in physics is ever completely solved, and anyone working in the field at the time would have said so readily. But the energy levels of hydrogen, the precise rungs on the ladder that its single electron could occupy, had been calculated using the best quantum theory available, and the result matched experiment with what seemed like satisfying accuracy. The equations produced numbers, the spectroscopes produced numbers, the numbers agreed. There was, in this agreement, a particular kind of confidence, not arrogance exactly, more like the quiet satisfaction of a calculation that closes cleanly. Hydrogen was the simplest atom. If the theory worked anywhere, it should work here, and it did, or it appeared to. The theory being used was Dirac's relativistic quantum mechanics, developed in the late 1920s. It was a remarkable piece of work. It combined quantum mechanics with special relativity in a way that hadn't been done before. And among its predictions was something striking. 2 specific energy levels in hydrogen, known as the 2s1/2 and 2p1/2 states, should be exactly degenerate. That is, they should have exactly the same energy. The electron in either state would sit at the same rung. No difference between them, none, down to whatever precision you could measure. This was a clean prediction, sharp-edged. The kind of theoretical result that feels satisfying in the way that a proof feels satisfying. Not approximate, not approximately equal, but exactly, rigorously, provably the same. Willis Lamb didn't believe it. That's not quite fair. He didn't disbelieve it either, not initially, but he thought the measurement could be done more precisely than it had been. The existing spectroscopic methods weren't sensitive enough to resolve the 2 levels cleanly. Lamb at Columbia University in the mid-1940s had access to microwave techniques developed during wartime radar research, and he recognized that these techniques could be applied to atomic spectroscopy with a precision that earlier instruments couldn't approach. In 1947, Lamb and his graduate student Robert Rutherford measured the hydrogen spectrum using these microwave methods. They found that the 2s1/2 and 2p1/2 levels were not degenerate. They were separated by a small but clear and unambiguous gap, roughly 1058 MHz, a frequency shift small enough to have hidden inside the resolution of earlier experiments, but large enough, once you had the right instruments, to be unmistakable. The 2 levels Dirac's theory said should be identical were not identical. The gap was stubborn. That's the word that keeps fitting. Not alarming, not dramatic, not something that sent the field into crisis, just quietly, persistently present. A discrepancy that sat between the theory and the measurement and did not go away when examined more carefully. The first response, as it usually is when experiment and theory disagree, was to look for the error, instrument calibration, systematic bias, some unconsidered effect in the apparatus. Lamb and Rutherford were careful, thorough, methodical, and the result held. The shift was real. Outside somewhere, a dog is barking at something insistently, then stopping abruptly, then silence. The kind of interruption that reminds you the world is still going about its ordinary business while you're inside thinking about hydrogen atoms. The Shelter Island Conference happened in June of that same year, a small gathering of theoretical physicists on the eastern end of Long Island, one of those meetings that turned out to matter more than anyone predicted when the invitations went out. Lamb presented his results there. Hans Bether, on a train back to Cornell after the conference, did the first rough calculation to explain the shift. What Bethe was trying to account for was the effect of the quantum vacuum on the electron in the hydrogen atom. The electron, sitting in its energy level, is not sitting in empty space. Or rather, it is sitting in the quantum vacuum, which, as the previous chapters have been working toward, is not empty. The vacuum fluctuations of the electromagnetic field, the zero-point fluctuations, the ground state activity that cannot be removed, interact with the electron. They nudge it. They cause it to jiggle slightly around its average position, and this jiggling alters the energy of the state it's in. The effect is not the same for the two s1/2 and two p1/2 states. The electron in the 2s1/2 state spends more of its probability distribution near the nucleus than the electron in the 2p1/2 state. Because the vacuum fluctuation effect depends on the electron's proximity to the nucleus, the closer the electron, the more the jiggling matters, the two states are shifted by different amounts. The degeneracy breaks, the levels split. The gap that Dirac's theory said was zero turned out to be non-zero because the quantum vacuum had not been included in the calculation. Bethe's initial estimate was rough. He knew it was rough. The full calculation required a treatment of quantum electrodynamics that was, at the time, still being developed. The renormalization techniques that would make QED one of the most precise physical theories ever constructed were worked out largely in the years immediately following the Shelter Island Conference by Feynman, Schwinger, Tomonaga, and others working through the problem from different directions. When those techniques were applied to the Lamb shift, the result was extraordinary. The theoretical prediction and the experimental measurement agreed to better than 1 part in a million. Then better still, as both theory and experiment were refined over subsequent decades. 1 part in a million. This is where I want to be careful about how the significance of this lands, because it is easy to say very accurate a prediction and let the phrase slide by without registering what it actually means. What it means is this: a theory that includes the effects of vacuum fluctuations on an electron in a hydrogen atom produces a number that matches what you measure in the laboratory to a precision of 1 part in a million or better. A theory that excludes those effects, that treats the vacuum as truly empty, produces a number that is wrong. Clearly, unambiguously, measurably wrong. The vacuum fluctuations are not optional. They are not a theoretical refinement that improves accuracy slightly at the margins. They are required to match reality. Leave them out and the atom doesn't behave correctly. Include them and it does. This is, as far as I can determine, the cleanest statement of what the Lamb shift actually demonstrated. The quantum vacuum is not a mathematical convenience. It is a physical entity. It acts on matter. It changes the energy levels of atoms in ways that can be measured and calculated and matched to extraordinary precision. The nothing nudging the electron, shifting its energy, leaving a mark, the 1058 megahertz gap between two energy levels that were supposed to be identical. That's what the vacuum leaves behind. Not a philosophical argument, not a theoretical extrapolation, but a number. Measured in a laboratory at Columbia in 1947, confirmed and refined and extended in the decades since. That only makes sense if the empty space around the hydrogen atom is not empty. Lamb received the Nobel Prize for the measurement in 1955. The citation described it, in the careful language of official recognition, as the discovery of fine structure in the hydrogen spectrum. What it was, more precisely, was the first clean evidence that the vacuum participates. The atom, after this, was no longer a closed system. The space around it, the quantum vacuum pressing in on every side, fluctuating, nudging, shifting, was part of the physics. The electron moving through its probability distribution was moving through something, not through nothing, and that something left a measurable trace. From a single atom, the question scales outward. If the vacuum acts on one electron in one atom with enough force to shift an energy level by a measurable amount, what does it do at larger scales? What happens when you sum its effects not over one atom but over all of space? What does the vacuum's energy look like when you step back far enough to see the whole universe? The number that comes back from that question is, to put it plainly, one of the most uncomfortable numbers in physics. Start with something you can hold. A hydrogen atom. One proton, one electron, the simplest arrangement of matter that qualifies as an atom at all. The electron sits in its probability cloud, the proton at the center, and between them and around them, pressing in from every direction, the quantum vacuum. Fluctuating, active, shifting the electron's energy levels by a small measurable amount. This much we have established. This much is confirmed. Now let go of the atom and step back. Step back far enough to see a molecule, then a cell, then a grain of dust drifting in a sunbeam in an otherwise empty room, then the room, then the building around it, the city around that, the continent, the planet. The vacuum is everywhere at every scale, unchanged in its fundamental nature, fluctuating at the same ground state level in the space between the atoms of your hand as in the space between galaxies. It does not thin out as you zoom outward. It does not concentrate anywhere. It is, to the best of current measurement and theory, uniform. The same energy density at every point, in every direction, at every distance. Keep stepping back. The solar system is mostly empty space. This is a fact that gets mentioned often and absorbed rarely. The distances between the planets are not merely large in the way that a country is large. They are large in a way that makes the planets themselves essentially negligible as a fraction of the total volume. The Sun, massive as it is, occupies a tiny portion of the volume enclosed by the orbit of even the nearest planet. The rest is vacuum, ground state fields, zero-point energy, distributed across an enormous volume of space that contains, in the material sense, almost nothing. Step back further. The Milky Way is a structure of somewhere between 100 and 400 billion stars. The uncertainty in that estimate is itself larger than the total number of stars that humans have individually observed in all of history, spread across a disk roughly 100,000 light-years in diameter and a few thousand light-years thick. Between those stars, more vacuum, more ground state fluctuations. The interstellar medium contains gas and dust, but at densities so low that a cubic meter of it contains on average fewer than a handful of atoms. For most practical purposes, the space between stars is as close to a perfect vacuum as anything in the observable universe gets, and the Milky Way is one galaxy among an estimated 2 trillion. The observable universe, the sphere of space whose light has had time to reach us since the universe became transparent, roughly 13.8 billion years ago, has a diameter of about 93 billion light years. It contains those 2 trillion galaxies, each with their hundreds of billions of stars, each star a dense knot of plasma and nuclear reaction. All of that matter, all of that energy in the conventional sense, photons, neutrinos, the kinetic energy of everything moving, the rest mass of every particle, add it up, every star, every black hole, every gas cloud, every planet, every cosmic ray, everything. It comes to roughly 5% of the total energy content of the observable universe, 5%. Here is the part that requires a pause. The remaining 95% is divided between 2 things that are not well understood. Approximately 27% is what cosmologists call dark matter, something that exerts gravitational effects on ordinary matter but does not interact with light, has not been directly detected, and remains unidentified despite decades of intensive search. And approximately 68%, the largest single component, the dominant constituent of the universe by a wide margin, is something called dark energy. Dark energy is, in the current standard cosmological model, the energy of the vacuum, not metaphorically, not as a rough analogy. The cosmological constant, the term in Einstein's equations that describes this component, has the mathematical properties of a vacuum energy, constant in space, constant in time, present everywhere simultaneously, not diluted by expansion. When the universe expands and the volume increases, the total amount of dark energy increases proportionally, because it is a property of space itself, rather than a property of the matter or radiation within it. The vacuum energy, everywhere, always, making up roughly 68% of everything. There is a glass on the windowsill nearby, left there from earlier, half full, the water inside perfectly still, and the light through the glass makes a small pale oval on the floor that shifts almost imperceptibly as the light outside changes. Something that's small and specific feels necessary when the scale of what we're discussing becomes hard to hold. Dark energy is not a force in the way gravity or electromagnetism is a force. It does not pull things together or push them apart in the way a localized source would. It is better described as a property of space, a constant energy density that exists wherever space exists, which is to say everywhere without exception. Its effect on the universe is not to attract or repel individual objects, but to influence the overall geometry of space-time, to contribute to the rate at which the universe expands. It is not matter. It is not radiation. It does not interact with light. It does not clump or concentrate. It simply is at every point, at every moment, in every direction, at the same density. Distributed is the word that keeps fitting. Not gathered anywhere. Not absent anywhere. The 68% figure, or 70% depending on the dataset and the analysis, is itself a measured quantity, derived from observations of the cosmic microwave background, the large-scale structure of galaxy distributions, and the luminosity distances to Type 1a supernovae. These are independent lines of evidence pointing to the same number. The figure is not a theoretical prediction extrapolated from first principles. It is an observational result. Something out there, constituting roughly 70% of the universe's energy budget, has been measured in its effects even if its nature remains unclear. Whether that something is precisely the quantum vacuum energy, the zero-point energy of all quantum fields, summed across all of space, is where the certainty stops. Because when theorists try to calculate the vacuum energy from quantum field theory and compare it to the observed value of the cosmological constant, something goes badly wrong, not slightly wrong, not approximately wrong in a way that further refinement might correct. The calculated value and the observed value disagree by somewhere between 60 and 120 orders of magnitude, depending on the assumptions made in the calculation. That number, that gap, is what the next chapter is about. There is a calculation that theoretical physics has been sitting with for decades. A calculation that produces a result so far from what is observed in the real universe that the gap between them has its own name, the vacuum catastrophe. And that name, for once, does not feel like an exaggeration. Here is the calculation in outline. Quantum field theory says that empty space has energy. Every quantum field in its ground state contributes a zero-point energy to the vacuum. There are many fields: the electromagnetic field, the electron field, the quark fields, the Higgs field, and others. All of them present everywhere, all of them fluctuating, all of them carrying their irreducible minimum energy. To find the total vacuum energy density, you sum these contributions, you integrate over all the frequencies at which the fields fluctuate, weighing each by its energy. The sum diverges. Without a cutoff, it gives infinity. This is not by itself alarming. Quantum field theories often produce divergent integrals that require careful treatment. You introduce a cutoff, a maximum frequency above which the theory is not expected to be valid, usually taken to be the Planck scale, where quantum gravity effects would presumably change the physics in ways the current theory doesn't capture. With this cutoff, the integral becomes finite. The number it gives is approximately 10 to the power of 113 joules per cubic meter. The observed value of the vacuum energy density, the cosmological constant measured through the accelerating expansion of the universe, confirmed across multiple independent observational methods, is approximately 10 to the power of -9 joules per cubic meter. Those two numbers need to be held next to each other for a moment. 10 to the power of 113 and 10 to the power of -9. The discrepancy is 122 orders of magnitude. 122 orders of magnitude means that the theoretical prediction is larger than the observed value by a factor of 10, followed by 121 zeros. There is no other instance in the history of physics, and arguably in the history of quantitative science, where a prediction and a measurement have disagreed by anything approaching this margin. The phrase "worst prediction in the history of physics" gets applied to it regularly, and without much contestation. It is, by any reasonable standard, the most embarrassing mismatch between theory and observation that currently exists in fundamental science. And it is not solved. I want to be precise about what this means and what it doesn't mean, because both things matter. It does not mean that quantum field theory is wrong. QED, which is part of the same theoretical framework, produces predictions that match experiment to 1 part in a billion. The standard model of particle physics, built on the same quantum field theory foundations, has been confirmed across decades of accelerator experiments with precision that is genuinely extraordinary. These are not the products of a broken theory. It does not mean the cosmological constant is wrongly measured. The observational evidence for dark energy, for the existence of something with vacuum energy-like properties dominating the universe's energy budget, is robust and comes from multiple independent sources. The number is not going away. What it means, and this is the part that remains genuinely, structurally unresolved, is that something in the calculation is wrong in a way nobody has identified. Either the cutoff is not at the Planck scale, for reasons not yet understood, or most of the contributions cancel. A phenomenon called supersymmetry could do this. If supersymmetry exists and is unbroken at the relevant scale, but no experimental evidence for supersymmetry has been found, or the vacuum energy does not gravitate in the way the calculation assumes, or the cosmological constant has a different origin entirely, unrelated to the zero-point energy of quantum fields. Each of these possibilities is a live theoretical option. None of them is established. There is somewhere in the ceiling of this building a pipe that occasionally makes a sound, a dull hydraulic clunk, irregular, not loud enough to be worth investigating. It has always been there. It will probably always be there. The building accommodates it by not resolving it. The history of physics contains several instances where a large discrepancy between theory and observation eventually resolved into a discovery, where the gap turned out to be pointing towards something new. The perihelion precession of Mercury, which Newtonian gravity couldn't account for, was resolved by general relativity. The ultraviolet catastrophe, the classical prediction that a hot object should radiate infinite energy at high frequencies, was resolved by Planck's quantization. Both problems, in retrospect, were symptoms of a deeper correct theory waiting to be found. The vacuum catastrophe might be like that. It might be pointing toward a theory of quantum gravity that doesn't yet exist, or a mechanism of cancellation that supersymmetry gestures toward but doesn't deliver, or something genuinely new that nobody has written down yet. The history gives some reason to think that problems this fundamental tend to have solutions this consequential. But I find myself wanting to be careful with that framing, and the care is not pessimism, it is just honesty. The vacuum catastrophe has been known in its modern form since at least the 1960s. It has been extensively examined. The brightest people in theoretical physics have worked on it for decades. It has not been resolved. The history of physics also contains problems that took much longer than expected, problems that resisted every approach brought to bear on them, problems that remained open for generations. This might be one of those. What makes the catastrophe specifically difficult, not just large but difficult, is that it is not a problem of missing data. It is a problem of two frameworks that each work extremely well in their own domains and produce, when combined in the most natural way, an answer that is catastrophically wrong. Quantum field theory works. General relativity works. When you apply quantum field theory's prediction for the vacuum energy to general relativity's equation for how energy curves space-time, you get a universe that looks nothing like this one. A universe that would have expanded or contracted so rapidly after the Big Bang that galaxies, stars, atoms, none of it would have had time to form. We are here, which means something must be cancelling most of that energy. The cancellation must be real. It must be precise to 120 decimal places, and nobody knows what is doing it. Precise cancellation to 120 decimal places is not the kind of thing that happens by accident. In physics, when you find a quantity that is fine-tuned to extreme precision, it usually means there is a reason, a symmetry, a conservation law, a deeper structure that enforces the tuning automatically. For the vacuum energy, no such structure has been found. The cancellation, if it is a cancellation, is either enforced by physics we don't understand yet, or the result of some selection effect in a landscape of possible universes, an idea that has its own deep theoretical and philosophical problems. This is not a comfortable place to stand. It is, however, where the physics currently is. Not approaching resolution, not clearly improving, sitting with a number that makes no sense and a gap that nobody has closed. The catastrophe is architectural in the end. It is not a mistake at the edges of the calculation. It is not a sign error or a unit conversion or a forgotten term. It is embedded in the most natural way of combining two of the most successful physical theories ever constructed. The problem is structural. The solution, if there is one, will probably require something structural in return, not a patch, but a different way of thinking about what the vacuum is, what energy is, what space is. Until then, the number sits there. 10 to the power of 113. against 10 to the power of -9. The gap between them is not a footnote. It is possibly the most important unsolved problem in theoretical physics. It is the place where two frameworks that each work brilliantly simply refuse, in the most fundamental possible way, to agree, and the vacuum, the nothing that turns out to be full, the ground state that cannot be quieted, the energy that cannot be removed and sits at the centre of it. Patient, unchanging, carrying a quantity that the best theories available cannot explain. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, one by Brian Schmidt and Adam Rees, published results from a years-long study of distant supernovae. They had been measuring the brightness of a specific type of stellar explosion, called a Type 1a supernova, at various distances across the observable universe. These explosions are useful to cosmologists because they have a known intrinsic brightness, a standard candle, in the technical language, which means that by measuring how bright they appear from Earth, you can calculate how far away they are with reasonable precision. The teams were measuring these distances in order to determine the rate at which the universe's expansion was slowing down. The expectation based on the prevailing cosmological models was that gravity, the mutual attraction of all the matter in the universe for all the other matter, would be gradually decelerating the expansion that began at the Big Bang. The question was how much deceleration, and what that implied about the eventual fate of the universe. What they found instead was that the expansion was not decelerating, it was accelerating. The universe is not just expanding, it is expanding faster and faster over time. The galaxies are not merely moving apart, they are moving apart at an increasing rate, as though some component of the universe is pushing outward, or more precisely, as though space itself is expanding with an energy that does not dilute as the volume increases. This was not a small surprise. It was, at the time, one of the most unexpected results in the history of observational cosmology. The two teams approached the data with some skepticism toward their own findings. The result was sufficiently strange that the possibility of systematic error, of some unaccounted for contamination in the sample, was taken seriously. The results held, independent confirmation followed. The acceleration is real, something is causing it. That something needed a name before it had a description, because that is how science often works. You name the effect while the explanation is still unresolved, so that work can continue, so that people can refer to the thing without having to describe the entire mystery each time. The name chosen was dark energy. Dark, because it doesn't interact with light, it doesn't emit, absorb or scatter electromagnetic radiation in any form. Energy, because it contributes to the universe's total energy budget and influences the geometry of spacetime in the way energy does. Together, the name sounds like a description. It is not. It is a label applied to an observed effect whose origin, nature, and mechanism remain genuinely unknown. The night outside has a particular quality right now. The air slightly damp, the street sounds muffled, as though the atmosphere is closer than usual, pressing in. Nothing to do with physics, just the specific texture of the hour. There is a candidate for what dark energy might be, and it is the most natural one available, the vacuum energy. The zero-point energy of all quantum fields, distributed uniformly across all of space, not diluted by expansion because it is a property of space itself, rather than something contained within space. This is the cosmological constant interpretation. Einstein introduced the cosmological constant as a term in his field equations in 1917 for different reasons, later called it a mistake. But the term and its mathematical structure survived, and the observed accelerating expansion fits neatly into a universe with a small positive cosmological constant. The cosmological constant has the right mathematical structure to be vacuum energy. It behaves the way vacuum energy should behave. It doesn't thin out as the universe expands, it remains constant in space and time. Everything about its observational behavior is consistent with the uniform energy of the vacuum, except the magnitude, which, as the previous chapter sat with at some length, is wrong by somewhere between 60 and 120 orders of magnitude, depending on how you do the calculation. The observed value of the cosmological constant is small, unimaginably, almost suspiciously small. The vacuum energy predicted by quantum field theory is not small. The gap between them is the vacuum catastrophe, and it has not gone away simply because we now have an observed quantity to compare against. If dark energy is the vacuum energy, it is a vacuum energy that has somehow been reduced from its natural value by a factor so enormous it strains any framework currently available to explain it. If dark energy is not the vacuum energy, if it is something else, some new field, some evolving component that merely resembles the cosmological constant, then the vacuum energy problem becomes stranger, because the question of where the predicted vacuum energy went becomes even more pressing. Neither option is comfortable. This is not, I want to be clear, a statement about the failure of physics. It is a statement about where physics genuinely is right now with respect to this specific question. The discomfort is real and acknowledged. It is not concealed by the field or minimized in technical discussions. The cosmological constant problem is openly described in the literature as one of the deepest unresolved problems in theoretical physics, and the discovery of dark energy did not solve it. It sharpened it, gave it an observed value to be wrong about, made the mismatch more specific and therefore more difficult to dismiss. There are alternatives to the cosmological constant interpretation of dark energy. Quintessence models, which replace the constant with a dynamic scalar field whose energy density evolves over time. Modified gravity theories that change the behavior of gravity at cosmological scales. Extra dimension scenarios. Various proposals involving the landscape of string theory and anthropic selection. These alternatives are not purely speculative. Some of them make testable predictions that current and near-future cosmological surveys are designed to probe. None of them are established. None of them are broadly accepted as the correct description. They are possibilities, held open by the fact that the most natural interpretation doesn't work. Dark energy, in this sense, is still what it was when the name was chosen, a label for something observed and not explained. The acceleration is measured. The component responsible for it is quantified. Its nature is unknown. This is the state of affairs described accurately. I find myself returning in thinking about this to the naming itself, dark energy. There is something instructive about the name, not in a critical way, but in an observational one. When you name something you don't understand, you're not describing it. You're giving it an address. You're saying, here is where the mystery lives, this is what we call it when we refer to it. We will continue working. The name is a placeholder, not a claim. Most of the great unresolved problems in physics have names like this. Names that sound like explanations but are, on examination, just addresses. The name tells you where to look. It doesn't tell you what you'll find. Dark energy is the dominant component of the observable universe. It makes up approximately 68% of the total energy budget. It is driving the accelerating expansion that will, over cosmological timescales, continue to push galaxies beyond the range where their light can reach us, gradually isolating the local group from the rest of the universe. Its effects are global, continuous, and utterly indifferent to the presence or absence of matter, life, or observation. and it is not understood. Not poorly understood. Not understood in outline with the details unclear. The underlying physics of what dark energy is, whether it is the vacuum energy, and if so, why it has its observed value, or whether it is something else entirely, is genuinely deeply unknown. The most careful theorists in the field say so plainly. The observations constrain what it can be. They do not identify what it is. The universe is accelerating. Something is causing that. The most natural candidate for that something is the energy of the vacuum. The same vacuum that the Casimir effect demonstrates is active, that the Lamb shift demonstrates acts on matter, that the uncertainty principle demands cannot be zero. All of those threads point toward a vacuum that has energy. The cosmological observations point toward a universe with a small, constant, space-filling energy. They should be the same thing. Whether they are is the question that remains open. It has been open for decades. It will likely remain open for longer than is comfortable to predict. The space between galaxies, the vacuum, stretching for tens of millions of light years between the nearest clusters, is not empty. Or it is empty in the material sense, while being full in the quantum sense, while being the carrier of whatever dark energy is. These descriptions do not contradict each other. They are all simultaneously current best understanding. What the vacuum is doing out there, in all that distance, in all that silence, at whatever the quantum ground state of every field amounts to across those scales, it is not nothing. It never was nothing. The question of what it actually is sits at the intersection of the two most successful physical theories humanity has produced, in the gap where they refuse to agree, patient and unresolved, and present everywhere at once, the same as it has always been, the same as it was before anyone thought to ask. Come back to the room, not any specific room, though a specific room is fine, whatever one is closest to where you are right now, whatever walls and floor and air are present. Just a space, a volume. The kind of thing that in ordinary life gets defined by what it contains: furniture, light, sin, temperature, the presence or recent presence of people. Now try to subtract all of that. Mentally clear it out. Remove the furniture. Remove the air. Remove the light, the warmth, the objects. Take the temperature down as far as it will go. Remove every particle, every photon, every trace of material content until the space is, by every ordinary measure, completely empty. What is left is not nothing. This is where the physics arrived, crossed the chapters behind us, through zero-point energy and Heisenberg's principle, and the Casimir effect and the Lamb shift and the cosmological constant. Not through a single argument, not through one decisive experiment, but through the slow convergence of independent lines of evidence, each one pointing to the same conclusion from a different direction. The vacuum is active. The ground state of every quantum field that exists is not zero. The space that appears empty, the space between atoms, between stars, between galaxies, carries an energy that cannot be removed because it is not stored in the space like furniture that could be taken out. It is what the space is. Every field present everywhere, all of them fluctuating, none of them ever fully still. The zero-point energy was in Planck's equation in 1911, patient in the mathematics long before the theory existed to explain it. The Casimir effect demonstrated in a laboratory that the vacuum between two metal plates is physically different from the vacuum outside them, different enough to exert a measurable force, different enough to move things. The Lamb shift showed that a hydrogen atom sitting in the quantum vacuum is not sitting in emptiness. The fluctuations press in on its electron, shift its energy levels, leave a mark precise enough to confirm to 1 part in a million. The cosmological observations showed that the dominant component of the universe's total energy budget is something with the mathematical properties of vacuum energy, distributed uniformly across all of space, driving an acceleration that will continue indefinitely. These are not four separate facts about four separate things. They are four windows into the same thing. There is a quality to late hours, something in how familiar spaces become more themselves when everything else is quieted, where the surfaces of objects seem slightly more present than they do during the day. The chair, the floor, the air in the room, nothing has changed. But the ordinary perceptual noise that usually fills attention has dropped, and what remains feels more textured, more specific, more there. The vacuum is like that in a way, though like is doing a lot of work in that sentence, and I am aware of its limits. It is not that the vacuum becomes more present in quiet moments. It is present continuously, uniformly, without variation across time or location. It was present before this room existed. It will be present after the materials of this room have dispersed into something else. The fluctuations running through the space between these walls are identical in nature to the fluctuations running through the space between galaxy clusters a billion light-years away. It does not concentrate anywhere. It does not thin. It simply is, at every point, whatever the ground state of all fields amounts to, which is not zero, which has never been zero, which will not be zero. What is harder to absorb, and this is personal, not rhetorical, is the implication for the concept of emptiness itself. Not the scientific revision of a technical term, but the deeper shift in what it means to point at a space and say, there is nothing there. There is no space in the observable universe to which that sentence applies. There is no region, however carefully evacuated, however thoroughly cooled, however far from any source of matter or radiation, where the quantum fields are absent. The fields are not material in the way atoms are material. You cannot scoop them out. You cannot shield against them. They are present in the interior of the most perfectly evacuated laboratory chamber, and in the intergalactic void equally, fluctuating at the same ground state level, carrying the same irreducible energy. The nothing you point at when you say, nothing is there, contains the ground state of the electromagnetic field, the electron field, the Higgs field, the quark fields, all of them, always. Whether this means nothingness is full depends still on what you thought empty was supposed to mean. That is not a deflection. The physics does not resolve the philosophical question. It only makes the philosophical question more interesting, more loaded, more difficult to wave away. If empty means containing no matter, then most of space is empty. If empty means containing no energy, then no region of space qualifies. If empty means absent of activity, absent of fields, absent of the ground state fluctuations that produce measurable forces and shift atomic energy levels, then empty, in that sense, does not exist anywhere in the observable universe. The vacuum is the closest thing to nothing that nature permits, and nature does not permit nothing. The Casimir plates move, the hydrogen electron shifts, the universe accelerates. 3 effects, 3 scales, 1 underlying fact. The space between things is not passive. It participates. It has always participated. The physics of the last century did not discover activity in the vacuum by looking for something exotic. It discovered it by looking carefully at the most ordinary condition available, space, emptied as thoroughly as possible, and asked what remained. What remained was the physics. It rests on this, all of it. The atom, stable in the vacuum's presence. The force between 2 plates with nothing between them. The expansion of space driven by something that fills the space uniformly. The term in Planck's equation that refused to be zero. all of it resting on the same foundation, that the ground state of a quantum field is not zero, that the minimum is not nothing, that the floor hums. The room after everyone leaves is not empty. It never was. This is where the narration rests. If these hours have meant something to you, if this particular way of sitting with physics has given you something worth keeping, then the most direct way to support it is through Patreon. This project has no corporate backing, no network, no external funding of any kind. Every episode exists because people who found value in it chose to contribute what they could. If you are in a position to do that, it matters more than you might think. The link is in the description, and if not, being here, listening, following along through 13 chapters on the energy of nothing, that matters too.